The next thing we're going to go into is collections of particles and rigid bodies. Essentially, a big part of this story is that there's not too much useful we can say about general collections of particles. If you're talking about like a blob of pudding or a bunch of marbles in a sack bouncing around, there's not too much we can say. There's one useful thing that we can say about general collections of particles. But if those particles are, if you can treat those as rigid bodies, if that's a reasonable assumption, and depending on what calculation you're doing, you know, that might make more or less sense for the same body. But if it is a reasonable approximation for your problem, there's a lot of stuff that we can say about rigid bodies. And so that's mainly what we're going to be talking about. So most of what we'll talk about relates to rigid bodies. The distinction that we're going to make as we go from particle dynamics to rigid body dynamics is that now the length of an object matters. So now, as opposed to particle dynamics, the length of an object and therefore its orientation matter. As a consequence, now we care about where loads are applied to bodies. We didn't care about that with with particles, because we're assuming that everything's just happening at a single point. But now, as a consequence, where loads are applied on a body affects its behavior. Okay, so before we go into that, what can we say about pudding dynamics? So where we're just talking about general collections of particles. So we're going to break this up into translational and rotational motion. Which is what we're going to do with all of rigid body dynamics too. Translational, we know surprisingly much about pudding dynamics with its translational motion. If you add up all the external forces on the pudding, that's equal to the mass of pudding times the acceleration of its center of mass. That's a surprisingly simple and useful relationship, considering that we haven't made any requirements on how these particles are connected. Are they bouncing? Are they connected by joints? So this is like, really? Wow. That's you. Rotational motion, we can't say very much. There's stuff we can say, but it involves doing calculations for each individual particle. And if you're breaking up pudding into, say, molecules, that's a pretty tedious exercise, you know. So what you can say relates to, relates external moments to angular momenta of each particle. And that's, unless you have some way to simplify that, that's just not a useful calculation to do. So what you can say is, you take this bag of marbles, throw it up into the air. If you keep track of the center of mass of all those marbles as they bounce around, the acceleration of that center of mass is equal to the external forces. That's a lot. The rotational stuff, there's not much we can say. But if you're comfortable making the rigid body assumption for your collection of particles, that's not a good assumption with a blob of pudding. But for any kind of engineering object or, you know, lots of objects that we're trying to calculate the motion of, it's a reasonable assumption. Right. Or maybe frozen pudding. That would be okay. So if you make the rigid body assumption, you can say a lot more. So here's what we know about rigid body dynamics. First, a rigid body is a collection of particles, so we know that that Newton's second law relationship still has to hold. Add up all the external forces. That has to be equal to the mass of the rigid body times the acceleration of the center of mass of the rigid body. And second, we know that if you add up all the external moments about a point A, that's equal to the mass moment of inertia about A times the angular acceleration vector. Okay, so this I is called the mass moment of inertia, and before we can do calculations, obviously I have to talk about what that is. And, okay, what do we know about this point A, that about point? In statics, that could be anything. In dynamics, we're severely limited in what that's allowed to be. And so, in a way, you know, the reason that we do statics before dynamics in the sequence is because it lets you focus on the left side of Newton's laws. You get used to free body diagrams, you get used to summing the external loads, and you don't have to worry about anything complicated going on the right side. But in some ways, it can give you kind of bad habits, and this is one of them. In statics, you can put that about point wherever you want. You can put it in the middle of the room, the corner of the object, whatever. Here, you only have two options. So A has to be either the center of mass of the rigid body or second, a point on the rigid body that's fixed in an inertial coordinate system. So what's an example of that? Like if you have a pin joint or a hinge or a ball and socket joint connecting the rigid body to the ground, then you can use this second one. The first one, okay, this one always works. You can always use this. The second one only works if you happen to have one of those cases. A point on the body is fixed in the ground coordinate system. Okay, so you might think, well, then if it's going to be a hassle to, sometimes it works, sometimes it doesn't work, maybe it'd be a better idea to just always use the rotational equation, the moment equation, about the center of mass. And you can do that. You always, whether there's a fixed point or not, you always can do it about the center of mass. But the equations, the system of equations you work with is quite a bit simpler if you happen to have a fixed point. So when we do have a fixed point, we are going to use that. You'll be happier when you do. If you don't have a fixed point, like you're doing the dynamics of a boomerang flying through the air, then you have to use the center of mass. Okay, so this one's easier, and so we're going to use it when we can. And so before we can start using these equations, here's a few things that we need to introduce. Before we use the moment equation. And by the way, I'm always going to abbreviate, Newton's second law, I always abbreviate N2L. This one I always think of as the rotational version of Newton's second law. And so I'm always going to write that Rn2L. I don't know. Nobody else does that. So, I don't know. So, that's what it means when, I don't mean that like nobody else does that. I came up with that. I just mean like that's not like a standard thing. I just do it because it saves time and lets me tell you what equation I'm on. So here's the list of things that we need to talk about. First, I'm going to talk a little bit about angular kinematics, rotational kinematics. of rigid bodies. We've already talked with circular motion about what angular velocity means and angular acceleration means. But those were in terms of particles, so I want to just, connect what it means for a rigid body to what it means for a particle. And then I need to talk about center of mass, how to calculate that. And then I need to talk about the mass, moment of inertia, about a point. People tend to talk about this just as the moment of inertia, so they leave this out, they leave this out. But you should get in the habit of thinking of this as the mass moment of inertia about a point. And here's why. Well, first of all, about a point. I mean, this thing isn't defined unless you choose your about point. The mass thing is important because in D form, one of the big ideas is the area moment of inertia about an axis and this one is also called, people just call it the moment of inertia. And to make it even more confusing, they abbreviate this I sub A exactly the same. Okay, so same abbreviation, even. Are you kidding me? And so because of that, these two things that mean totally mean different things, because they're called the same thing and they're abbreviated the same way, it ends up being something that people are constantly confused about, even though they don't have any relation to each other. So that's why you need to remind yourself this is the mass moment of inertia. It has to do with the resistance of an object to rotation. This one that you use in D form has to do with the resistance of an object to bending. Okay, so we're going to go through, we're going to do these things. Any questions about that setup? Was that really necessary, for example? All right, so let's talk about rigid body kinematics first. I won't spend a lot of time on this. I might finish this by the time we have to stop and do the quiz. So rigid body kinematics is very closely connected to circular and spherical motion. And here's why. Because if you have an object, why did I make such a hard object to reproduce? God dang it. I'm erasing that. Okay, how about like a gourd? That I should be able to do in two different orientations. Okay, so say that this object is rotating about this point here, this way. Okay, and say that you're tracking, let's track the motion of this point through that rotation and this point through that rotation. This point follows a circular path around the axis. This point follows a circular path around that. Okay. And that's not because I chose 2 points where that works for. That's just a property of rigid bodies. As they rotate around an axis, every path sweeps out a circle, or if it's not in a plane, it follows a spherical shell. Okay, so every point in a rigid body rotation is in circular in 2D or spherical in 3D motion. If you represent the angular position of a rigid body, about its axis of rotation, by theta, and you can think of that as a function of time, then the angular velocity vector as a function of time is equal to the time derivative of that angular position. And actually, let me be a little more clear about this. So let's first just think about this in plane motion. Okay, so if you represent the rigid body angular position as an angle theta about its axis, so this is just for plane motion, then the angular velocity is equal to theta dot, and the angular acceleration is equal to omega dot. And this works in 2 dimensions for any rotation. In 3D, there's no such thing as an angular position vector. So we have to sort of skip that first step. But the angular velocity, the angular acceleration, is still the time derivative of the angular velocity vector. missing a dot. Thank you. That would be weird if they were the same. Okay, so 2D versus 3D. Even though there's no such thing as an angular position vector in 3D, the angular velocity vector is really a vector with a direction along the object's instantaneous axis of rotation and so its direction is along the axis of rotation. That narrows it down to this way or that way. And you choose the one that satisfies the right-hand rule. So this happens according to the right-hand rule. In the xy plane, the angular velocity vector is always equal to 0, 0, some scalar omega. Okay, so here are some examples of how this works. So say you have some random object, and it's rotating about this point. So first, if this object is rotating that way, this is the x-axis and this is the y-axis, then the angular velocity vector is equal to a scalar value, omega, times the unit vector 1, 0, 0, because the axis of rotation is this way, right, one way or the other, and according to the right-hand rule, it's in the positive x direction. If it's rotating let's say this way, then the angular velocity vector, this time the right-hand rule says it has to be in the negative y direction. So this would be omega times 0, negative 1, 0. And then last, if it's rotating about this axis, let's say it's at 45 degrees, then the angular velocity vector would be the scalar omega times the unit vector 0.7071, 0.7071, 0. One important thing to recognize is that a key difference between translational quantities and angular quantities for a rigid body So let's say translational velocity and acceleration versus angular quantities, omega and alpha, is that on a rigid body, the velocity and acceleration vectors, translational, vary from point to point. On the other hand, the angular velocity and angular acceleration hold for the entire rigid body. Once you know the angular velocity and the angular acceleration at an instant for a rigid body, you can calculate that the translational velocity and translational acceleration of any chosen point using the velocity cross product equation and the watermelon equation. The velocity is equal to omega cross r, and the acceleration is equal to all ripe watermelons will rot. And these are true in both 2D and 3D. This is the oh man. Okay, this is the last thing I want to say. If the rotation isn't about a fixed point, then the equations above are combined with the relative motion equations. So the velocity of the point relative to the ground is equal to the velocity of the point relative to usually the center of the rigid body, but that could be anything where you happen to know this, plus the velocity of the center relative to the ground, and then the acceleration. So just like with circular motion, with rigid body motion, relative motion comes up really naturally in a lot of cases. Okay, any questions about that? I'll do an example first thing next time.